right, class. Let's design and conduct an experiment to discover Newton's second law of motion. I don't know why that's written twice. Who cares? Okay, so the deal with this learning objective is it all has to do with a lab. And in our lab, we performed an experiment. And there were two experiments that you could perform. Here's this first experiment. Let's look at it. It looks like we have net force, mass, and acceleration. And in this case, the experimenter doubled, oh my gosh, let's zoom in here. They doubled the net force each test. So they started with 2 newtons of force on the object. That was a doubling. And then they changed the force again to 8 newtons, and that was a doubling. And what did they do to the mass in this experiment? They kept it constant at 2.0 kilograms. So in this case, this was the independent variable, this was the constant, and acceleration is the dependent variable. And what did they notice? They got an acceleration of 1 meters per second for this first trial, 2, and then 4. So when they doubled the net force, they noticed that the acceleration also doubled. Okay? That is the definition of a direct relationship. So they just discovered that net force and acceleration have a direct relationship. The other lab experiment that the student could perform was they could have kept the net force constant, and in this case, this person kept the net force constant at 4 newtons each trial, and they changed the mass. Looks like they started with 1.5 kilograms of mass, and they doubled the mass each test. And, if you push on a mass, it's going to accelerate, and they push it with 4 newtons, and the mass of this first test was 1.5 kilograms, and they measured an acceleration of 2.67 meters per second squared. So again, this is the constant in this experiment. The mass is the independent variable, and the acceleration is, again, the dependent variable. So the two different experiments switch the constant and the independent variable. And what do they notice? If they double the mass each test, the acceleration halves times 1/2 or times 0.5. That's the pattern that you're supposed to recognize. When one variable doubles and the other one halves, that is a straight up inversely proportional relationship. Cool. That's what Sir Isaac Newton did, and he was able to write a law. That's his second law. So let's recall Newton's laws real quick. So his first law, an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by a net force or a net external force. We'll review what net force means later, but just think, if you want to move an object, cause motion, you have to use a force, or cause an acceleration, you have to use force. Newton's second law of motion, this is the one that was discovered in those experiments that we did. So the acceleration of an object is directly proportional to the net force on that object, and inversely proportional to its mass. That we just did. We just looked at that. So net force and acceleration have a direct relationship. Mass and acceleration have an inverse relationship. It's an equation. Newton's second law is an equation. So let's write it in here. Acceleration is directly proportional to the force and inversely proportional to the mass, or net force would probably be more accurate. Okay, so when I write it as an equation, it's harder, or we will learn to see this as not just an equation, but as an entire sentence or as an entire concept. So let's draw a couple arrows on this, and we'll do this a bunch of times in this class. Acceleration and force have a direct relationship, and acceleration and mass have an inverse relationship. So this equation actually represents a concept, and that is Newton's second law. Okay? So we can write acceleration, force, and mass in an equation. Once we can do that, then you can start to do a lot of cool stuff. You can predict the acceleration of objects. You can predict the force that you'll need to move an object with a specific mass. This is how we get to Mars, people. Get excited. Okay, Newton's third law. You guys know this one. That's not what we're learning in this objective, but let's just remember it from middle school. Newton's third law. For every action, there is an equal and opposite reaction. That's what we learned in middle school, and that's great. That's not bad. But in high school, a better way to think of it is every force is a pair where each force is equal in magnitude but opposite in direction. We're going to be learning about this thing called force pairs when we get to Newton's third law. Okay, numerators and denominators. You can recognize a direct relationship when one variable is in the numerator and the other variable is also in the numerator. Look at that wonderful handwriting. Numerator. Is it numerator? Yeah, it is. Oh my goodness. Let's just do this. Numerator. We can write here, Mr. Rip. Numerator. Okay, let's look at that equation again. Acceleration is directly proportional to the force, but inversely proportional to the mass. Look at force here. It's in the numerator. Cool. Acceleration, it's not in a fraction at all, but we can assume that this is in the numerator. Okay? So, why? Because, we can create a fraction. We can go a over 1, or acceleration divided by 1, because a over 1 equals a. Anything divided by 1 is itself. So we can, anytime we see a variable or even a number by itself, we can assume that it's in the numerator, because we can create that fraction over 1, and it's going to be, it's going to stay the same amount. Those arrows are super helpful. See how we have these, we're pointing from the A to the F to say that, look, they're both in the numerator. If the best way to see this relationship, other than by looking at that data and doing the experiment, is let's just look at these symbols here. Imagine if I increased the force on an object. I'm making the force bigger. Well, in order for this equal sign to stay true, this acceleration also needs to become greater. Let me look at just an example with numbers. I think some of you guys might have a better time just thinking about this as if it was just numbers. For example, if we had 5 equals 10 over 2, that is a true, that equal sign is a true, this is a true mathematical statement. 5 does equal 10 divided by 2. But if I make this 10 bigger, not in size, but actually in number, if I make it, 100, I've just increased that thing in the numerator, that quantity in the numerator. What happens to this 5? Well, this also has to increase in order for it to be a true statement. And in fact, 100 divided by 2 equals 50. Way more than 5. A factor of 10 more than 5. Okay. So in order for this to say true, if you increase something in the numerator, the thing on the other side of the equal sign will also increase. So that is the mathematical logic behind this sort of a model where we're not using numbers anymore. We're using these letters or symbols which represent a variable or represent an actual quantity that occurs in nature, like force or acceleration. Cool! Let's look at that other one. You can recognize an inverse relationship when one variable is in the numerator and the other variable is in the denominator. Denominator. So, acceleration Remember that we assume that this is in the numerator because it's not part of a fraction, and if it's not part of a fraction, you can easily make it a over 1 and it stays the same, and now it's really easy to see it's up there in the numerator of that fraction that we just created, and that's fine. I can do that. I'm allowed to do that mathematically, but mass down here, look at you, mass, hanging out in the denominator all by your lonesome. Now mass, whoop, I lost my fraction. If I increase the mass, I'm going to decrease the acceleration. Ooh, ba-bam. In order for this equal sign to stay true. So these two guys, acceleration and mass, one's in the numerator and one's in the denominator, and this represents an inverse relationship. And we saw that in the data. Remember, when we doubled the mass, the acceleration halved. This was a direct relationship. So that's the idea behind this Newton's second law. If the variable is not part of a fraction, you can assume it's in the numerator. If it's not part of a fraction, you can assume it's in the numerator, because it can be, 5 is the same as 5 over 1. And look, it's in the numerator now. Good. It is not the same as 1 over 5. We can't just throw that 5 to the denominator. We're not allowed to do that. 1 divided by 5 is like a decimal. I don't know it in my head. Woo! Rearranging Newton's second law. All right, folks. This is where you're going to use your homie, algebromy. Your bro, algebra. And algebra has some rules, dude. Algebra's got some rules for your friendship with your algebra. I don't know what I'm doing here, guys. I'm just trying to have fun. So look at these different ways of writing Newton's second law. What? We just did this whole thing, and you did all those little numerators and denominators. Why are you throwing these new things at me? Don't you worry, baby birds. I'll feed you. These are all the same thing. They are all the same law. It's just the letters are rearranged. Let's take this one over here, and let's write it in our own writing. F equals mass times acceleration. Force equals mass times acceleration. Now, say I wanted to isolate a variable. Like, say I wanted to solve this equation for the letter A, for acceleration. I can do that using algebra rules. So right now, is A isolated? Nah, it's not. This M is bothering it. Get away, M. So what we have to do is let's write down our steps here. We want to isolate the variable. That's cool. That's step 1. Step 2 is you have to use opposite, I don't know, functions? Is that the right thing? I don't know. We'll just say it. Opposite functions. For example, right now, M is bothering A by way of multiplication. So how do we get rid of the M? We have to divide. So you always use the opposite function. So what happens here is these guys cancel out. You guys know this from algebra. And now A is by itself. But don't forget rule number 3. Whatever you do to one side, you do to the other side. I don't want to write the whole thing. One side, other side. One side, other side. Whatever you do to one side of the equal sign, here's my equal sign here, you got to do to the other side. So when I divided this whole side by M, I got to divide this side by M. Nothing cancels out on this side, but let's just bring this thing down and see what we get. We get F over M equals A. And oh my gosh, wouldn't you know it, you have these independent variables over here on this side, and you can see that same old Newton's second law relationship again. So it works any which way as long as they're one of these different ways. So you can rearrange it in different ways. just depending on how you use your algebra. And you can isolate the variable, use the opposite function. Remember one side, the other side thing, and that's how you do that. Solving Newton's second law problems. Okay, here's the last thing that we're going to do. A 2-kilogram soccer ball experiences a net force of -6 newtons. What is its acceleration? Okay, so we have to solve for acceleration. We actually have to plug in numbers and know things now. So I always draw it. Why not? Here's a soccer ball, and it experiences a net force of 6 newtons, and it says it's negative. Look at that, how I realized that it said negative like last second. So -6 newtons. So this soccer ball is experiencing a net force. It could have maybe like a force of friction in this direction and a kick in this direction, but the net force is -6 newtons. So when we add the forces together, our net force, and we could use this little backwards 3 looking thing, that means net force. We learned that in a previous video. The net force equals -6 newtons. And we know that the soccer ball is 2 kilograms, so I can write M equals 2 kg. And then all you got to do is use Newton's second law. It's asking for acceleration. So let's use one of these equations that has acceleration already isolated. Let's use that one. A equals F over M. Now, I'm going to use my homie algebromi again. My algebro. I can make that a better F for force, or net force is the more accurate way of saying it with Newton's second law. And I'm going to plug in the things that I know and solve for what I don't. So I know the force is -6 newtons, and I know that the mass is 2 kilograms, and I get -6 divided by 2 equals -3, and it's an acceleration. In physics, you never forget your units, meters per second squared. So what I did there is I used the power of substitution. Substitution. Just like you can substitute a soccer player in for another soccer player, you can substitute in the value for the symbol when you are solving. So I substituted in that -6, and then you can see instead of writing the F, I wrote that -6 up top. So that's how you use substitution to solve for Newton's second law type problems. You got it, people.